In this unit, we focus on monosaccharides, specifically looking at how we convert from the open chain linear monosaccharide to a ring monosaccharide. What we see in nature in living things is that there is an equilibrium between an open chain form of the sugar, such as the D-glucose that we talked about in the last unit, or other open chain sugars that we focused on so far, and a cyclic form, a ring form that forms spontaneously. It is not a process that requires an enzyme in order to occur. It's just something that's going to occur in solution. So when a sugar is in solution, such as the solution of the cell, it's going to reach an equilibrium between the cyclic and acyclic forms. And we can take a look at that now in a bit more detail. So we are going to, as an example to get us started of the conversion between acyclic sugars and the cyclic monosaccharides, we're going to use our old friend, D-glucose. And in this non-enzymatic process, what's going to happen is that we are going to reach an equilibrium. You'll see I've drawn the equilibrium arrow slanted toward the product side, toward the cyclic form side, because at equilibrium, when we think about the equilibrium between the acyclic open chain form and the cyclic product, we're going to see that the equilibrium is generally going to favor that cyclic product, particularly if the cyclic product has 5 or 6 carbon atoms in it, which is really common when we're looking at these 6 carbon atom sugars, such as glucose. So let's take a look at what's going to happen here. What's going to be particularly favorable is that the oxygen atom at that penultimate position, remember the penultimate position is the next to the last position of the chain, where we think of the first position of the chain as being this carbonyl group of the aldehyde. Then we go to position 2, 3, 4, 5, and 6. So this next to the last position, position 5, that hydroxy group acts as a nucleophile, a source of electrons. It's going to come up and find this electrophilic carbon, the carbonyl carbon that's positively polarized, and form a covalent bond to it. So the carbonyl carbon is acting as the electrophile. The oxygen here at the penultimate carbon is acting as the nucleophile. So what will go on is that the nucleophilic oxygen comes up, and it is going to come up and form a covalent bond here to the carbonyl carbon. That's going to force the electrons from that pi bond to go up onto the oxygen. And since this reaction is occurring intramolecularly, intra meaning within the same molecule, it's going to yield a ring. So we are going to be forming a ring that's going to link this oxygen atom that I've got highlighted with my laser pointer here up to what starts off as the carbonyl carbon. And then this is all going to be connected through, as well as I'm highlighting with my laser pointer, back over to here. So we're going to end up making a ring. And to think about how many atoms are going to be in that ring and the structure of that ring, I'm going to map that out by putting numbers on these atoms. So I'm going to start with the carbonyl group there and call that carbon number 1. I'm going to come down the chain to carbon 2, 3, 4, 5. And then I'm going to go ahead, and since that oxygen atom here is going to be part of the ring, I'm going to call that number 6. And so we have 6 atoms here that we've numbered. They're going to be part of this continuous system. So our 6 atom ring, we need to go ahead and draw over on the right. And that 6 atom ring is going to have 5 carbon atoms, as we see 1, 2, 3, 4, 5, and a 6th oxygen atom. A common way to draw these cyclic molecules with 6 atoms in the ring, including an oxygen, we put that oxygen in the upper right-hand position right here. And I will then go in and number these 6 positions, 1, 2, 3, 4, 5, 6, corresponding to the numbering of the acyclic form. So you will notice in the acyclic form, as we look at how the ring is forming, that position 6, that oxygen atom that I'm highlighting here, linked to carbon number 1, the aldehyde carbon. So that is why when we come over to here, I have position 6 linked to position 1. So the bond that I'm going to highlight in red here in our cyclic form is the newly formed bond that we got by linking the nucleophilic oxygen with the electrophilic carbonyl carbon. Now we need to go in, since we've numbered the carbon atoms of this ring, and fill in the branches that are coming off of that. And we are going to use, for purposes of this structure, we're drawing what's called a Fischer projection as our way of representing the stereochemistry of the molecule and who's connected to whom in here. The Fischer projection is a little different than the typical 6-atom ring chair conformation that you may remember from your organic chemistry days, and that in a Fischer projection, we illustrate the groups that are bonded at each position as these lines to speed along the process of drawing out the configuration. So I've drawn in these vertical lines here, and the ends of those vertical lines will fill in with the hydroxy groups and hydrogens at all of these different positions along the chain. So at position number 1, right here, we would have directly bonded there the oxygen atom, which will be part of the ring. That's the guy right here. And additionally, we would have another oxygen that was originally the carbonyl that's not part of the ring, and a hydrogen that's also not part of the ring. So I'm going to fill those in by filling in H and OH. Now, in this structure, the hydroxy group at position 1 and the hydrogen at position 1 could be flipped in their orientation, meaning that you could put the OH group up top and the H group down below. Since this is a non-enzymatic process, actually both scenarios in actuality occur. We'll get into that a little bit more later. The reason why both scenarios occur, that the hydroxy group can be oriented down or up at position 1, is because when this reaction is taking place and that hydroxy group comes in and attacks the trigonal planar flat-laying sp2 carbon atom of the aldehyde, that is going to create a new chiral center at position 1. Position 1 is not initially a chiral center, it's a trigonal planar carbon, but it becomes tetrahedral as a result of this reaction. And in the reaction, there's no preference for this oxygen to attack from the front of the molecule or the backside of the molecule. And so as a result, you can end up with the presence of multiple configurations here, that the hydroxy group can be either oriented downward or oriented upward here. There's no preference due to the fact that the starting structure that this originated from was a trigonal planar carbon that could be attacked from the top side or the bottom side, therefore giving ultimately these groups that are bonded there as branches, either orientation, either top or bottom. So the configuration does not matter there at position 1. It could in fact be either configuration. It could be hydroxy group up or down at that position 1. On the other hand, as we go around the ring, when we get to positions 2, 3, 4, and 5, the configuration is essential. It is essential to show this in a specific way. So specifically, what's going to be the case when we go to draw these around that ring is that atoms that appear on the right in our initial acyclic form are going to be downward oriented in the ring. So atoms that are on the right in this acyclic Haworth projection structure are going to become atoms that are oriented downward in the Fischer projection cyclic form. And so we can go in and fill in the parts and pieces of the ring this way by thinking about position 2 has the hydroxy group on the right, hydrogen on the left. That means that the hydroxy group position 2 has to be oriented downward because it's on the right. So we'll go ahead and fill that in. Hydroxy group on the right, hydrogen is the other missing component there, so we fill that in up top. At position 3, we use the same strategy. So at position 3, the hydrogen is on the right. That means that the hydrogen is oriented downward in the cyclic form, and the hydroxy group is oriented upward. So let's go ahead and do that. Atom on the right at position 3, that's the hydrogen is oriented downward per the definition of how to draw these. And the hydroxy group, which was on the left at position 3, has to be oriented upward. We follow the same theme at position 4. Our structure, ask yourself, is the hydroxy group going to be up or is it going to be down? Think about that for a sec. And hopefully what you are thinking is that the hydroxy group should be oriented down at position 4. Then we come to position 5, and at position 5, if we are working with a D amino acid here, that means that the CH2OH there that was oriented here at the very end of the chain is going to be oriented upward. If this were a D amino acid or D configuration sugar, and it is. And then that leaves in the downward position the hydrogen that was bonded at position 5. So the hydrogen at position 5 is oriented downward here at position 5, CH2OH oriented upward because this is a D sugar, and that's the way that that's going to come out to play in the Fischer projection. The oxygen here, keep in mind, is the one that came around and formed the ring. So that's the oxygen that's part of this ring here. So this is going to be our Fischer projection way of going about drawing the cyclic monosaccharide. Now, if we have the hydroxy group oriented downward, as we see here at position 1, I mentioned earlier that that hydroxy group at position 1 is variable in configuration. The configuration of that, up or down in other words, is not locked into place because of the way that the reaction occurs. That the reaction is occurring to create that chiral carbon at carbon number 1 from scratch. So that has variability. And due to that variable configuration, we have two possible structures that can result from cyclizing D-glucose. We have the one that I have already drawn, this structure right here. We also have a structure that is completely identical except for at position 1, having the hydroxy group up rather than down. So the other possible cyclic configuration of D-glucose, due to the way this reaction takes place, that we have the nucleophilic hydroxy group attacking the trigonal planar carbonyl group, is that we could take that position 1 hydroxy group, and rather than that being oriented down, as I'm highlighting with the laser pointer here up top, is it could be oriented upward. Everything else around the ring is going to stay the same as the structure up top because all of these positions, positions 2 through 5, have fixed configuration because they're a specific configuration of the starting structure, and nothing is directly happening at any of those carbon atoms. So there's no way to change the configuration of that from one stereoisomer to another. So going around the ring, I'm just copying the information from up top down below here. And if I've done this right, then what I have done is that all of the groups here from position 2 through 5 are oriented the same way in the top structure as the bottom structure. The only difference between the two structures is that variable configuration of the hydroxy group at position 1. So as a consequence of this, position 1 is a position of this structure that has some additional terminology associated with it to make it clear which of these structures we are talking about when we cyclize the D-glucose, because both of these structures, the top one and the bottom cyclic form, both exist. So to distinguish between the two, we have some specific terminology that we use to refer to that carbon number 1. First off, a term that you need to be aware of here is the term anomeric. The term anomeric refers to sugar molecules that differ in the orientation of the hydroxy group at carbon number 1 and at no other position within the molecule. We would refer to those structures as being related as anomers. So we could refer to the two compounds that we've drawn out here as being anomers of one another. Anomers differ at the anomeric carbon. So the anomeric carbon is carbon number 1 with variable configuration. So these anomers differ in configuration at only one position within the molecule. All the rest have the same configuration between the two structures. So only one position differs in configuration. And that one position that differs in configuration is what started off as the aldehyde group, carbon 1 in our open chain form, becomes this variable position in the cyclic form. And these different cyclic sugars, since the exact stereochemistry dictates biological function, can have different biological functions. So that's why we make a fuss about this and we take a look at it. So to describe in words the configuration at the anomeric carbon, we use the terms alpha and beta. Alpha is going to refer to the anomeric carbon where the hydroxy group is oriented downward. So an alpha sugar is going to refer to the hydroxy group at carbon number 1 is oriented downward. Beta is going to refer to that hydroxy group at carbon number 1 being oriented upward. So looking at the Fischer projections that we have drawn here and here, what I want you to do is hit pause for a second and ask yourself which of those will we classify as the alpha and which will we classify as the beta. So thinking about what we classify as the alpha versus the beta, our structure where we have the hydroxy group oriented downward is going to be referred to as the alpha. So here up top, since the hydroxy group is oriented downward at that position 1, we refer to that as alpha. And if the position 1 hydroxy group is oriented upward, we refer to as beta. So beta is going to be the configuration of the structure down below. We could also keep in mind functional group terminology as a throwback to some of your organic chemistry. Keep in mind that the functional group that's present here at carbon number 1 is a hemiacetal. So you could also refer to this as the hydroxy group orientation at the hemiacetal functional group. A hemiacetal functional group was a functional group where you have a hydroxy group directly bonded to a carbon and an ether group bonded to that same carbon. So position 1 here is a hemiacetal group because it has a hydroxy group and it also has an ether group, an oxygen directly connected to another carbon there as we go around the ring. So alpha and beta are the two ways to describe this based on the orientation of the hydroxy group. So that is one way that we can go about describing these. There's some additional terminology that I should make you aware of here before we finish off this unit. And that additional terminology that you should be familiar with as I move this over, or try to move this over just a little bit, is that we have some terms that we can use to refer to structures that are ring sugars. And those are based on how many atoms are in the ring. And based on the number of atoms in the ring, the typical themes that we'll see is 6 carbon atoms in the ring. 6 atoms in the ring. One of those atoms is an oxygen. So 6 atoms in the ring is a common theme because that allows the atoms in the ring to have pretty ideal bond angles for sp3 atoms. And those 6 atoms in the ring, if it's a sugar, are going to be referred to as pyranoses. The pyran part is indicated there's 6 atoms that are in a ring. The OSE indicates that this is a sugar. The other common theme that we'll see is 5 atoms in a ring. And if there's 5 atoms in the ring, we refer to that as a furanose. And the way that I remember a furanose is furan, sounds like 5 because it starts with an F. So that's a way to help you in remembering that. Furanose 5, pyranose 6. And so to illustrate that these glucose molecules are in the cyclic form, what we do is build a name that incorporates the term glucose, so gluco for glucose, and then indicate after that pyranose indicating that it is in the 6-atom ring structures, the specific one that we are referring to. So pyranose refers to the 6-atom ring, and that differentiates this structure from the open chain form of glucose. The gluco part there indicates that this is derived from glucose. And then other terms that we can plug in there to further emphasize the structure here is we plug in the term D to indicate that this is the D stereochemistry sugar. And then finally, alpha or beta to indicate the configuration of that anomeric carbon, the carbon that is part of the hemiacetyl group, in other words, or another way of describing it, carbon number 1. So alpha D-glucopyranose would be the name that we could use to refer here to the structure up top. We could use that to refer to the structure up top because we said that was the alpha configuration. We drew that based on the open chain form of D-glucose, so the D-gluco part is going to work out, and then the pyranose refers to the fact that there's 6 atoms in the ring there. So what we're going to do in the next video is we will be continuing to look at these concepts by doing a couple of example problems where we're given some model open chain sugars and asked to convert them into the cyclic form, or we're given a cyclic sugar and asked to convert it into the open chain form to make sure that we're up to speed on this. So stay tuned for that.